Hi folks, I wanted to talk through some of the more interesting solutions to this homework, some of the problems on page 1068, and um, show you how some nice abbreviations, you might say, but really systematic use of symmetry actually is really helpful. So 3b shouldn't have been too hard. 5b though brings us to a very special vector field. What they're talking about here is the unit radial vector field. They're taking xi plus yj plus ek and dividing it by r. Um, and so we want to be smart about that. We'll be able to do with a few preliminary calculations, some of which we've seen before, we'll be able to do it in a very slick way. And I'll show you two slick ways. And yeah, so usually we've called the square root of x squared plus y squared plus z squared rho to distinguish it from just root x squared plus y squared. But as I've mentioned before, a lot of time that gets called r as well when there's no confusion. So so one thing we noticed a while ago was that the partial derivative of r with respect to x, very simple calculation, turns out to be x over r. That one calculation, and the same ones for y and z, that's really actually the only place you actually ever have to put square root of x squared plus y squared plus z squared if you use the rules nicely. But that takes practice. Okay, so if you did it with a lot of square roots, it's okay. But I'll show you how to do it without. Now notice that if the r derivative is x over r, the y derivative is y over r, the z derivative is z over r, when you put those together as a vector, you get 1 over r times the radial vector field. So it's actually the unit radial vector field. So the gradient of the r function is the unit radial vector field. Now they happen to be interested in the divergence of exactly that vector field. So in fact, what they're actually calculating is the divergence of the gradient of r, which is the Laplacian of r, but they don't sort of tell you that. Okay, so the divergence is the derivative of the x component with respect to x, y component with respect to y, etc. We do have to use the quotient rule here, but when we take the derivative of the bottom, the denominator, that's the derivative of r with respect to x, and that's that x over r. So that's where you don't need any square roots, etc., etc. R squared, of course, is just, you write that as r squared. Put things over a common denominator, all over, well, first multiply by r over r and everything, put things over a common denominator, and you get, magically, you get an r squared. So that partially cancels. That'll be much more interesting if that actually totally canceled, and we're going to see that happen very soon for a somewhat different radially symmetric vector field. Here, the divergence turns out to be 2 over r. Now, if you look at the cool rules in like 23 through 30, some sum and product rules, in particular number 25, the product rule for the divergence, you can get something nicer. And also, there's a rule. I'm realizing, I don't know why I didn't realize this before, that in 16.1 they really should bring in the chain rule for the gradient. So let me just introduce that. You have one of our favorite situations. You have a function of 3 variables that is some interesting function of 3 variables, and then put into just a function of 1 variable. So it's this very standard chain rule situation. The tree is particularly simple, and we know how to do the chain rule there. And what it happens if we do the gradient is actually very pretty. So we're going to take the derivative of that composed function with respect to x and y and z. When you take it with respect to x, that outer function, you just get the ordinary derivative f prime, of course evaluated at g of x, y, z, times the partial of g with respect to x. If you want to draw out the tree, it's not a bad practice, but it's one of the simpler cases. Same deal with y and z, and the key is that you always get the same factor in front, f prime of g. So that's just the gradient of g times an f prime of g out front. Okay, so the gradient of f of g is f prime evaluated at g times the gradient of g. Very, very natural kind of chain rule. So I'm going to use the combination of those to make this pretty slick. This is a good example of kind of working through, you want to look at this line by line carefully to see what's happening in every line and get used to the idea that this is slick and really is much more powerful eventually. So we're taking the divergence of a product. That's what number 25 says something about. That's the function in front times the divergence of just this vector field. Sorry, just the r, plus the gradient of the function in front dotted with the vector field. Not too shocking that dots should come in here. Okay, and this is similar to what I was talking about in the previous video about how you derive these guys. So we'll assume that's true. The divergence of R is really simple. That's actually one of the ones in number 30, but it's just super simple. It's the dimension of the space you're working in. Here it's 3. So that's times R to the minus 1. Then I'm going to use that the cool chain rule for the gradient here. Derivative of anything to the minus 1 is minus that thing to the minus 2. That's just one variable derivative, but then times the derivative of what's inside, the right kind of derivative of what's inside, which is the gradient of R, and then that's going to be dotted with R. Okay, notice what's going on here. This is a scalar function times a vector field, then dotted with another vector field. So this dot can be done first, and then eventually multiplied by the R to the minus 2. Doesn't really matter the order. It's one of the fundamental things about scalar multiplication and dot products and stuff like that. Okay, now gradient of R, that's what I summarized before. That's the vector R over the scalar R, the unit radial vector field. So those combine to be R to the minus 3, and then R dot R, the vector field dotted with itself, the magnitude squared of the radial vector field is R squared, and then it just simplifies to 2 to R to the minus 1. Very slick and worth looking at, especially for problems like number 30 and beyond, when we'll do those more, because it's really a lot slicker than grunging out a whole lot of square roots. Okay, the next couple are pretty easy. I think I'll take a look and see if people need specific help with this, but I do want to mention one thing. We're getting a little bit ahead of ourselves in a way. We took a lot of time to figure out that if a vector field satisfied in 2 dimensions satisfies the scalar curl is equal to 0, that didn't always mean it was conservative. It meant that it wasn't obviously non-conservative. In this section, they kind of cheat a little bit, and they give you a theorem that says if the curl of f is equal to 0 and the vector field is defined on all of R3, very special case, no possibility that there's anything we take out of our universe, then they're claiming it must be conservative. That should feel a little bit weird without some powerful theorem to show it. We were not able to show an analog of that without Green's theorem in the plane, and we got the notion of like simply connected versus not simply connected for the domain. So there's really something going on here. I would say just say the curl f equals 0 calculation, just like in the plane, says it's not obviously non-conservative. And then you really actually need to check, and especially if there's anything weird with the vector field. I think my annoying alarm is beeping. So, just a few more things. Okay, so we find f in 3 stages because it's a 3-variable function. We do one antiderivative. You have a quote constant that's really a function of 2 variables. Then you plug that back in to carefully see what has to be true about the second function. Then you get a function of 1 variable. Let me know if that's a difficult part. 15 was very similar. 23, best way to do that is just write down the left-hand side, expand that out. Here, you can kind of recollect everything in different order, and it just equals div f plus div g. Try not to get backwards logic here, and I can talk to people about that if I see backwards logic coming in. And here, I just didn't finish the calculation. As I mentioned, the divergence of R is just the number 3. 30b is a really good one to do with the product rule for the divergence. You get the function R coming out times the divergence of the vector field R. Then you get the gradient of the function R dotted with the vector field R. Gradient of R, again, is R over R. Very slick. Here, the Laplacian. We saw that a little bit before with about the heat equation and things like that. Here, we're interpreting it as a 2-stage thing. We take the gradient of a function, and then we take its divergence. And that's a very natural thing to do. Here, I'm using the chain rule for the gradient, and then simplifying that a little bit. Here I'm using the fact that the gradient of R is vector R over scalar R. That kills the square there. And then using the chain rule for the divergence. Again, you don't have to do this. You can grunge it all out with the x squared, y squared, z squared, but it's so elegant if you do it this way.